Hello everybody. So in our series of lectures on basic electronics, learning by doing, let us move on to the next one. Before we do that, we will recapitulate quickly what we discussed in the previous lecture. You might recall that we discussed about the different feedback configurations in an operational amplifier, and we looked at some of the specific configurations and how they lead to specific types of different amplifiers. So in that last time we discussed about current amplifier or current to current converter, current controlled current source, ICIS. Then we discussed, after the feedback, negative feedback, we discussed why operational amplifiers are called operational amplifiers, because they can perform different types of mathematical operations on electrical signals. So we discussed some of the mathematical operations that can be performed with the operational amplifier, and out of that the first one we discussed was multiplication by a constant, which is in principle a very simple amplifier, a linear amplifier. The output is some A times the input voltage. That means the input voltage is multiplied by a constant factor called A, which is otherwise known as the gain of the amplifier. So a normal voltage amplifier, it can be considered as an amplifier which is capable of performing multiplication by a constant. That is what we saw. We saw two simple configurations. One is non-inverting amplifier and the other one is an inverting amplifier. So we also actually performed an experiment on the inverting amplifier. Then we also discussed how by giving full feedback we can get unity gain. So the gain becomes unity, but even then it is a very useful circuit because it can be used as a buffer. What I mean by that is, this amplifier, even though gain is not the main concern, it offers a large input resistance and a very small output resistance. Therefore it can be used as a buffer amplifier, unity gain. Now let us continue with our discussions on the mathematical operations. I just want to show you the same set of operations that we discussed last time, the different types of operations. For example, the first one is already what we have discussed, multiplication by a constant, something like y is equal to k times x. In this case, in an amplifier, voltage output is equal to k times voltage input could be a simple voltage amplifier with a gain of k here. Then we can also add two signals, which is called a summing amplifier. So y, for example, is equal to k times x1 plus x2, and with the value of k equal to 1, this becomes a simple summing amplifier without any multiplication factor. So you can think of an amplifier, V output is equal to some gain times, where the gain can also be 1 or any larger number, multiplied by the sum of the inputs V1 plus V2. So when I have this type of an amplifier, I call this as a summing amplifier, because the output is proportional to the sum of the input voltages. We have taken typically here two signals, but in principle you can have more than two also. You can have 3, 4, whatever number that you require. So this is one circuit which perhaps we will discuss in detail today, and there is also another amplifier called difference amplifier. If you can sum two signals, in principle it should be possible for us to find the difference between the two signals also, which are connected at the input. So a difference amplifier, the output will be proportional to the difference in the inputs, the two inputs. I have taken two typically example. V output is k times V1 difference V2. If V1 is larger than V2, you know that it will have a positive value, and therefore output voltage will be positive. If V1 is less than V2, then you would get a negative result here, and therefore output voltage will have a negative value. So, whatever may be the thing, the output is proportional to the difference between the two inputs V1 and V2. Therefore, this amplifier is called difference amplifier. You have other operations which we also mentioned last time, an integration where the output voltage is an integral of the time integral of the input voltage, as well as differentiation where the output voltage is the time differential of the input voltage. These two, if there is enough time, we will look at this time, otherwise we will take it up in the next discussion. So, what is a summing amplifier? How do you construct a summing amplifier? The construction of the summing amplifier is very simple, as you can see on the screen now. You have got, you already know, if I have one resistor here with one voltage, this becomes a simple inverting amplifier. Now, what we have done is we have added one more resistance in parallel, and we give the V2 input in parallel to V in V1. So, they are connected together to that this point, which is also called the virtual earth point, because the other input, the plus input of the op amp, is grounded. Therefore, there cannot be very different voltage on the negative input, because this difference cannot be larger than plus or minus few hundred microvolts that we have already seen. And therefore, if this is going to be 0, this is going to be very close to 0 within plus or minus few microvolts, few hundred microvolts. And therefore, this is a virtual earth point. I would like you to remember that, because it will be useful to understand the working of the summing amplifier. So, you have two inputs here, V1 and V2, connected to two resistors R11 and R12, and their feedback resistor is R2, and you have the voltmeter to measure the output voltage. So, this is a very simple configuration of a summing amplifier. Right, but in principle I also mentioned to you that you can have more than two inputs. You can have 3 inputs or 4 inputs as you require. Now, to understand the summing amplifier, it is nice to recall a known circuit for you. I hope every one of you can recognize. The first one I have shown here is, what is it? It is a current to voltage converter. Is one of the feedback configurations that we discussed, and therefore, you have a I in here, and the output voltage V out is equal to minus R times I in, where R is a feedback resistance. So, this circuit is a well known circuit, we have already discussed, we have demonstrated also. Now, what I am going to do is, because this is a virtual earth point, I can add multiple current inputs to this point. That is what I have done in the next circuit that you can see in the figure. So, I have connected I1 as well as I2. So, what is going to happen is, because the current going through the op amp is very, very small, which is called the input bias current, about which we will discuss a little later, this current, which is actually flowing into the op amp, is going to be a very, very small magnitude, and therefore, the entire current I1 plus I2 by Kirchhoff's current law will have to go only through the feedback resistor. Very little component, small component only flows through the op amp, and therefore, almost the entire current I1 plus I2 start moving through R, and because it is moving towards the output terminal, the output voltage should be minus, and the voltage here that you measure is between the output point and the ground, and because this point is as good as the ground, is a virtual ground, therefore, the voltage developed across the resistor is the voltage that you would measure here, that is the voltage with reference to ground, and therefore, it will be minus R times I1 plus I2. So, the two currents combine together and flow through R and produce a voltage which is minus R times I1 plus I2 by simple Ohm's law. So, this is a current summing amplifier. This amplifier is summing the two currents I1 and I2, and the output therefore is proportional to current I1 plus I2, the sum of the currents. Therefore, we are going to exploit this idea by introducing a voltage source V1 and a resistance, which can, because this is a ground point, the current through that will be only decided by R11. Therefore, the current here is V1 by R11, that is a current I1 now. Similarly, you have a V2 here and R12 here, because this is a ground, you have V2 by R12 as a current I2 flowing through the second one. So, we know output is minus R times, whereas the R is a feedback resistance, R times I1 plus I2. Now, we have got we have obtained I1 I2 by using two voltage sources V1 and V2 and two resistors R12 and R11, and therefore, now if you look at it, V output is equal to minus R by R11 V1. Basically, V1 by R11 is the current I1 multiplied by R is the voltage due to this current, plus V2 by R12 is the second current I2 multiplied by R gives me the second voltage. So, I sum these two voltage because I have to sum the two currents, sum these two. Therefore, if R11 is R12 and is also equal to R1, if I take it as R1, if the two resistors become equal for simplicity, then output voltage is, I can take out this R by R1 minus R by R1 multiplied by V1 plus V2. If I also make R is equal to R1, then this factor will become 1, the multiplication factor. Then the output voltage is the sum of the two input voltages V1 plus V2, but there is a negative sign which shows that it is going to be 180 degrees out of phase. You can also have DC or AC inputs. So, whatever may be the thing, the instantaneous values at every point will be the sum of the two instantaneous inputs V1 and V2. So, V output is equal to minus R by R1 V1 plus V2, that output is proportional to sum of the input voltages. So, it is a very simple way to obtain the output voltage in terms of the input voltages. So, this is basically a summing amplifier. So, let me just quickly do a simulation of the summing amplifier. So, you have a breadboard and you have the dual supply here one end, and you have two voltage sources. You can see that it is a one box in which two voltage sources are there, they can be increased or decreased, and you have a multimeter to measure the output voltage, you have the op amp and the various resistors, etc. And this is the summing amplifier circuit that is shown here, same as what we just now discussed. You have R1, R2 and R2. This R3 is basically to compensate for the differences in input bias current and things like that. So, right now we need not bother too much about that. So, the basic idea is you have one voltage here that produces a current V1 by R1, there is another voltage V2 that produces a current V2 by R1. These two currents add here at the virtual edge point, and that flows through the feedback resistor. Therefore, you get an output voltage which is the sum of the two currents, proportional to the sum of the two currents, and the currents are produced by two voltages, and therefore, ultimately it becomes sum of the two voltages. So, let me quickly build the current circuit. So, you can see the op amp goes and sits in the proper place, and the different resistors are put in place, and the wiring is carried out. Right. So, you can see the pin number 4 is connected to the negative, the blue line. The blue line is the negative of the power supply, and the red line is the positive of the power supply, that is connected to pin number 7 of the op amp, as you can see, and the black is the ground that is connected to one of the rail lines here. This is and that is also connected to the negative of the multimeter. Right. Now, the pin number 2, you have one resistor, which is another resistor is connected to pin number 2 also, but they are connected to two different sources. This red line comes from one voltage source, the other red line comes from the other voltage source. They are adjacent points, but they are different, and the common ground is all connected to the same ground line. So, two voltage sources are connected to the input, and this is connected to the ground. The pin number 3 is connected to the ground, as it is shown here in the circuit, and this feedback resistor is here, and that is connected between as a feedback resistance between pin number 2 and pin number 6. Right. So, the wiring is exactly similar to what you have seen here, and therefore, now we are ready to perform the experiment. We will switch on the dual power supply, we will switch on the voltage sources, and we will also switch on the multimeter, which is also connected between the pin number 6 and the ground to measure the output voltage. Now, let us start giving input voltages in millivolts. Let me increase here, this is about 100 millivolts, and this is 0, and because the gain is 10, the gain is 10, this is the feedback resistor is 10k, the input resistors are 1k each, therefore there is a gain of 10. So 100 millivolts multiplied by 10 is 1.1, because I have not given the other input anything. Now if I give another 100 millivolt here, it has become 100 plus 100, 200 millivolts together. So this 100 millivolt and this 100 millivolt will have to be summed together at the output with a gain factor of 10. So when you do that, you get about 2.2 volts. So you can see, if I keep increasing the voltage, the output also changes to some 3 volts or 4 volts. This is 200 millivolt input, another input 200, so output is proportional to 400 millivolt, 400 this is 10 times multiplication is there, and therefore it becomes 4 volts, right. So the slight difference that you get in terms of an additional value here can be accounted for in terms of the tolerances of the resistors. The resistors may not be precise, and there is also what is known as an offset voltage. Every op amp can have some finite voltage at the output, even when the two inputs are connected to the same voltage or connected to the ground. This voltage we call offset. So this offset voltage, that means it is already having a residual voltage of about 400 volts, 400 millivolts, and therefore when you connect the output comes in combination with that additional offset voltage. That is why it is showing 4.4 volts and things like that. So it is a very, very simple configuration, one can easily do the circuit, and I have also got some data here where you can see how the different numbers come. So it is not important, maybe when we do the actual experiment we will be able to see that. Now once I get a summing amplifier, then you can immediately imagine that this can be used in different situations. For example, in case I need an average voltage of all the voltages that I have with me, then it must be very easy to do. So for example, in the circuit I have shown V1, V2, V3, 3 input voltages are there, and I have got everywhere 3R, 3R and 3R as the resistors, and R is a feedback resistor. Now what will be the output voltage? This is the same summing amplifier, the only difference is the input resistors are 3 times the feedback resistor, all of them are equal and 3 times the feedback resistor. So the output voltage will have to be minus V1 plus V2 plus V3 by 3, because you find this is R, this is 3R, the output will be 1 by 3 times V1. The output at the second input is V2, that again is 1 by 3 because R by 3R. Feedback resistor is R, input resistor is 3R, the amplification or the gain factor is R by 3R. Similarly for the third one, it is R by 3R. So when I combine them together, you find minus V1 by 3, minus V2 by 3, minus V3 by 3, that means minus of V1 plus V2 plus V3 by 3. So what is this? This is nothing but the average of the 3 input voltages. V output is an average of 3 input. You also should remember that there is a negative sign that shows there is a phase difference between the input and output. So from this is another mathematical operation that you have now determined, that is to get the average of the 3 input voltages, right. Now we will try to do the demonstration of the summing amplifier. Now here I am sure you can see the circuit of the summing amplifier with V1 and V2 and the 2 resistors and the feedback resistor all in place. This is a voltmeter. So you can see in the breadboard the actual operational amplifier and the 2 resistors at the input and the R3 which is connected to the ground from the pin number 3, and this is the feedback resistor which is here. So you can see the circuit is the same as what you have seen here and what also you have seen in the simulation. So this is a basic summing amplifier with 2 inputs. Now, to get the 2 inputs, you can see I have connected one voltage source. This is a voltage source, and you can change the voltage input from millivolts to volts, and that is connected to the breadboard as one of the input, and that voltage is also monitored by this voltmeter that you see here. It is kept in voltage mode, and what you read is the voltage applied from this voltage source. Right now it is in 300 millivolts is the voltage that I apply here, and therefore it is also reading 0.3 volts, 0.30, that is nothing but 300 millivolts. 0.3 volts is 300 millivolts. If I now change it to 200 millivolts, then it shows 0.2. If I change again back to 0.3 or 300 millivolts, the multimeter reads 0.3. So, you can see this voltage source and voltmeter is corresponding to V1, first of the 2 inputs. The second input is got from a power supply, part of the power supply, which has got a variable input here, and that voltage is connected as the second input on the breadboard. This red wire is corresponding to the second input, and this multimeter, I am sure you are able to see that, is the input voltage corresponding to this power supply here. So, I have 2 independent power supply, one from this and the other from the voltage source, and this voltmeter reads the second voltage input V2. So, both are connected, and the output is monitored by a third multimeter which I have connected here, and this is the reading corresponding to the output voltage, and that is connected to the third multimeter. Now, if it is a summing amplifier, I have given here around 300 millivolt. So, you can see it is a 0.3 volts or 300 millivolts, and here it is about 300 and odd. This is something like 330 or something. So, together if you add, you should get about 600 and odd, and what you get in the third multimeter is the sum of the two, 0.68, because in the circuit, if you observe, I have used all of them 10K, 10K, 10K. Therefore, the gain factor becomes 1 here, and therefore, output is simply the sum of the two, and I would draw your attention to the sign on this multimeter which shows minus. Therefore, these two inputs are positive, but at the output you get a inversion, because it is minus R times V1 plus V2 or R2 by R1 or whatever, and therefore, it is the minus sign comes because it is there is an inversion involved at the output. Now, you will observe when I change the input voltage of one of the voltage source to 400, that is 0.4 volts or 400 millivolts plus whatever that was previously there, 3.7 or so, together makes it 7.78 or 780 millivolts. So, you can see every time I change these two, the sum of the two is what I get at the output. So, I will keep decreasing. I would like you to look at this and also this. So, 0.3 plus 0.37 or so gives me 0.68, and 0.2 and about 0.37 gives me about 0.57, and now I am going to still reduce it. This is 0.1 here, V1, V2 is about 0.37. So, together it should be around 0.47, and this reads 0.48. So, the two voltage sources connected at the input and the output is the sum of the two voltage inputs. Therefore, this becomes a summing amplifier. Having seen the demonstration of the summing amplifier, now we can also look at some of the applications. Already we have seen one circuit which is an application of the summing amplifier. Do you remember that? Yes, that is the averaging circuit. We have seen the averaging circuit where the output voltage is an average of the input voltages V1, V2 and V3 as an example. Now, we will see one more example which is of great importance, and that is a digital to analog converter. So, what is a digital to analog converter? A digital to analog converter is something like a circuit that is shown here in the form of a box. You have digital input. The digital input is having only two values, either 0 volts or 5 volts, or in terms of numbers 0 or 1, logic 0 or logic 1, and this output here is a continuously changing number or voltage in this case. So, what is that we want to do? We want to convert a digital number. In this case it is a 4-bit number, where a 4-bit means binary digit. It can be either 0 or 1, 4 of them. So, you can have, as you see on the screen, 0 0 0 0, all zeros to all ones. You can try all permutations at the input. You would find there are nearly 2 power 4 possibilities, that is from 0 0 0 to 1 1 1 you have 16 possibilities of different numbers. There, if you equivalent decimal numbers, if you look at, it will be 0 to 15, because the weights for 1111 is 8421. If you add them all together, it is 15. So 8421 is 15, 0 0 0 to 15 is the number that I can send here for different inputs, and what I get will be a proportional analog voltage. So it converts a digital number into a corresponding analog voltage. For example, if I send 0 0 0 0 as it is now, you get V is equal to 0, output is 0 obviously. But if I send 1 1 1, all these inputs 1, that means 5 volts if I connect everywhere, this is a digital input, then output will become some maximum value, for example 15 volts. So if I send a number 3 corresponding to a bit pattern 0 0 1 1, which is 3, if I send, I will get 3 volts. If I send a pattern corresponding to 8 1 0 0 0, the output voltage will be 8 volts. So if I keep changing here the number, there is a proportional corresponding analog voltage here, and that this is what we call a digital to analog converter. So if I want to bring about this circuit, how to construct a circuit which will perform what I just now explained to you. That means if I give a digital input with 4 inputs, either it can be 0 or 5 volts, nothing else in between, then I should get a proportional voltage which is proportional to the particular number that I send here. If I send 5, I should get 5 volts. If I send 7, I should get 7 volts, etc. So that is what I have shown here in the graph onto your bottom. You can see on the x-axis I put the number n, which is the digital number that I send in 4-bit format, and what I get on the y-axis is the output voltage. So here you can see that for every number I change here, there is a corresponding change in the output voltage. So when I keep changing the number continuously from 0 0 0 0 to 1 1 1 1, you would find that the voltage keep increasing by small amount every time I increase the count. Therefore what I get here will be something like a staircase. For every number that I have here, there is a corresponding level of voltage, analog voltage. If I increase the number by 1, it increases by a small value, and if I increase to still further, it increases by the next number, and so on and so on. So if I have here in this case 4-bit, I can go up to 15 here, and the output voltage will correspond to the corresponding analog that I get here. So you find in this example, when I send a number 7, I get 0.875 as the voltage, and when I send 15, it will be 1.875 volts and things like that. So this is what is called a digital to analog converter in a simple way. So how do we implement this? So now what I can do is I can take a summoning amplifier as I did before, but there are certain very specific differences. In the sense, I have used resistors R for one of the input, I have used 2R for the second input, I have used 4R for the third input, I have used 8R for the fourth input. That means the resistors are according to the weightages of the binary digits. So this is the most significant bit, as it is known as, and this is the least significant bit, and therefore you would find the corresponding resistors are also changed accordingly. Now, I think I should put it like this. This is the least significant digit and this is the most significant digit. The least significant digit gives you a least current. So, the current here is voltage divided by resistance by Ohm's law, V0 by 8R, and if I call V by R, V0 by R as I0, then it is I0 by 8 is the current in this. Because here it is 4R, this ohm, the current produced when I have V1 applied is I0 by 4 because of the 4R, and in the third line it will be I0 by 2, and in this it is I0. So, you have the currents here which are proportional to the binary positions of the value, positional value of the digital number, and therefore, these currents are going to be summed here, and that will be what will be proportional to the V out. So, V output is going to be minus, just now we have seen I1 plus I2 plus I3 plus I4, these all should be I2, I3 and I4 times R, and in this case I1 is I0, I2 is I0 by 2, I3 is I0 by 4, and the last one is I0 by 8 multiplied by R. So, this is the voltage that I will get when I apply all of them with 5 volts. If I apply all of them with 0 volts, there will be 0 currents. So, the entire current will be 0 multiplied by R, the output voltage will be 0. So, the maximum voltage is when I apply all the voltages here, all the 4 voltages, and that will correspond to this current. Now, therefore, what is the gain factor for each of the thing? For A3 it is minus 1 because it is just R by R, minus R by R, that is equal to minus 1. For the second one is minus R by 2R, therefore, it is 0.5 for the second one, minus 0.5. For the third one it is R by 4, therefore, minus 0.25, and the last one it is 1 by 8, so minus 0.125. So, these are the gains by which I should multiply the input voltages, and that is how I will get my proportional analog voltage. So, the input voltage are two states, either 1 or 0 in logic, or either 0 volts or 5 volts. Right, there are 16 possibilities from 0 0 0 to 1 1 1. So, when I have all input 0, the output voltage is 0, as I already explained to you. When only one of them is high, that is the least significant bit is 1, that means I will have 0 0 0 1 in binary, the output voltage is only multiplied by 0.125 times the R1 R by R, because R by R is 1, it is just 0.125 voltage minus. When the signal is 0 0 1 0, the binary number is 0 0 1 0, then the output is corresponding to the second point, which is minus 0.25, and therefore is minus 0.25 volts, and so on. So, you can see the output voltage is proportional to the digital number, magnitude of the digital number that I connect at the input with the 5 volts or 0 volts, as the case may be in terms of binary digit. And therefore, when I get all the inputs 1 1 1 1, the output is maximum, that will have 1, 0.5, 0.25 and 0.125 all together coming and summing together, and therefore, you get minus 1.875 volts. So, that is what you will get when the input is all of them are 0, all of them are 1, and this corresponds to 7, that means this alone is 0, rest of the things 1, and therefore, you get 0.875 volts. So, this is actually a digital to analog converter. Now, what I am going to show you is actually a demonstration of the digital to analog converter. I will go down to the table and show it to you, the working of the digital to analog converter. Here you can see the circuit diagram of the digital to analog converter. You have 4 input resistors, and they are all 10K, 20K, 40K and 80K. They have to be R, 2R, 4R and 8R. So, the R is 10K. So, 10K, 20K, 40K and 80K. You have the 4 inputs here, V0, V1, V2 and V3, and you have the summing amplifier here. This is a feedback resistor which is also 10K in this case, and we measure the output. So, in order to give the digital number here, what we have done is we have used this 10k etc. by standard values. We have used 10k here. For this we have used two resistors, two 10k resistors in series. That is what you will see here in the circuit. For the sake of 40k, we have used 33k and a 6.8k resistor together, so in series, so that together they form 40k. And for 80k, we have used 47k and 33k in series, two resistors. So you can also buy from the market very precise values of resistors and try them out. So it will be much better in performance. Now these are the resistors, and in order to give different binary inputs here, what we have done is we have constructed a clock circuit using NE555, and it is a very low frequency clock. As you can see from the light emitting diode here, it is growing very slowly. So this is 1 hertz approximately, and that is given to a counter, a binary counter 7493. So this binary counter output will go from 0000 to 1111 in a sequence regularly every time a clock input comes, and those 4 outputs 000 to 1111 is now connected to by using these wires to the input of the binary here V0, V1, V2, V3, and therefore what is going to do is it is going to keep on counting. As you can see from the light emitting diodes that are connected to the output, you can see that all of them are now glowing, all of them have gone 0. Now this is the first one 1, this is 2, this is 3, 1 1, then 100 is 4, 101 is 5. So it goes in binary sequence here. As it goes, the input will keep increasing. So the summing amplifier output is measured using this multimeter. You can see that this voltage, whenever there is a change here, is also changing the output voltage here. It goes one after another. So you can see that. Now what we have also done is, in order to, what is going to happen now, because it is going in a sequence, this output voltage will keep increasing in a sequence up to a maximum and then again come to 0, etc. To see that, we have actually, instead of looking at the multimeter, we have taken the output and connected to an oscilloscope here. So this is an oscilloscope, and the output of the summing amplifier is now connected to the oscilloscope. I am going to connect it, and then for increasing the speed, I am going to remove the capacitor here and connect the small capacitor which I have here, I hope. Now here I have removed the earlier capacitor, which is about 100 microfarad, and replaced with a very small capacitor 0.1 microfarad. Therefore you can see the frequency of this LED is glowing has increased enormously now. You can only see the most significant bit flickering, rest of the things are not flickering because they are all also going in the sequence, but because they are going at a very high frequency, you are not able to see them, and this only you are able to see a little bit of the second digit, but you are not able to see rest of the things. So now the changes are too fast, and therefore the output voltage will also keep increasing in a staircase type of a thing. That is what you see on the oscilloscope here. You can see the voltage is increasing, and this is actually on the negative side, therefore you can see it is increasing on the negative side. Okay. So this is the corresponding output of a digital to analog converter when you have continuous change from 000 to 111 with you using a counter. So you get a staircase generated here. It is a negative going staircase, that is what you get, and therefore this becomes a digital to analog converter. Instead of giving this continuous input, I can connect them to specifically to 5 volts or 0 volts as a number that I want, and the output will be a constant value corresponding to that at this stage. Because I am continuously changing here, the output voltage is also continuously changing. So this is an example of an application of the summing amplifier with a digital to analog converter. Now next we will move on to the next mathematical operation. We have already completed the summing amplifier, and now we will move on to the next application of the operational amplifier, which is a differential amplifier or difference amplifier. It is, you have seen the summing, then you should look for the subtraction. Okay. And so basically what is a difference amplifier? That I have shown on the screen a very simple configuration of the differential amplifier or difference amplifier. You can call it by any name you want, and you can see that op amp, you have got two resistors R1 and R2 as it is in the non-inverting inverting amplifier, for example R1 and R2, and you also have another R1 R2 on the other non-inverting input. So this becomes the difference amplifier or differential amplifier, because the output voltage V0 is equal to some constant A times V2 difference V1, where V1 and V2 are the two input voltages. So you see that in the previous summing amplifier, the two different voltages were applied to the same terminal, the negative terminal. In this case, the two inputs are connected to, one to the negative inverting input, the other to the non-inverting input. So you have A into V2 difference V1. If V2 is larger in magnitude to V1, you get a positive answer, positive voltage at the output. If V2 is less than V1, you will get a negative output voltage. So it actually is, therefore the output is proportional to the difference in the two input voltages. You can, there is an advantage in using this type of difference amplifier or differential amplifier, because you can see it only is sensitive, it is sensitive only to the difference in the voltages between the two inputs. So all the inputs which are common, they are called common mode signal. Can you imagine the voltages which are common to the two inputs? You can immediately recognize all the extraneous noise voltages that is around us due to the 50 cycles, due to the various other sources. You would find all of them will be common to both V1 and V2. In addition to whatever voltage you apply, there is also going to be the noise voltages due to the surroundings. All of them, because they are common, they will, and they are common to both the inputs, they will never be appearing at the output in principle, because this amplifier is only looking for the difference between the two inputs. Whatever that is common, therefore will be rejected. Therefore this difference amplifier has got a great advantage in terms of noise rejection, and that factor basically in a difference amplifier is called by a figure of merit, which is called common mode rejection ratio, which is a ratio of the differential gain to common mode gain, AD by AC. We will talk more in detail about this CMRR and the other parameters of the operational amplifier at a later time after we discuss the mathematical operations. So basically the difference amplifier, the output voltage is proportional to the difference between the two input voltages. Now to understand the relationship between the output and the input in terms of the circuit, I have given a very simple scheme here. So you can see V output, the same circuit is drawn in a slightly different way, that is all. It is the same, there is no change here between the one that I showed you before, it is the same thing. Now V output is R2 by R1, where R2 is the feedback resistor, R1 is the input resistor, which is common to both V1 and V2. We have used the same resistor, equal resistors, R1 and R2. R2 by R1 multiplied by V2 minus V1 is the output voltage. The output voltage is proportional to the difference, we have already seen. Now how do we get this expression for the output? It is possible by using superposition theorem. You assume that V2 is not there, so you ground the V2 input and apply only V1 and find out what is the output voltage. Then what you do? You apply only V2 and ground the V1 input and find out what is now the output voltage. Then by superposition theorem, the total output voltage when the two inputs, both the inputs are present, will be the sum of these two outputs, and that is what we want to do now. So the first figure here which I have shown, I have grounded the V2 input and there is only V1 input, and when I ground this R1 R2 at the plus terminal, they are coming in parallel, and therefore this becomes a very simple inverting amplifier. As you can see, the configuration is identical to an inverting amplifier. Therefore, the VO1, which I call corresponding to V1 alone being there, VO1 is equal to R2 by R1 times V1, because it is an inverting amplifier. There is also a minus sign here, minus R2 by R1 times V1. This is what it is a very simple expression that I got only when V1 is applied, when V2 is grounded. Now we will do the other thing, that means ground the V1 terminal and apply only the V2. Now what happens? When you do that, you can immediately see you are applying a voltage V2 across two resistors in the potential divider arrangement. R1 and R2 are coming in potential divider arrangement, and therefore I can easily calculate what is the voltage at this point, V2 prime. So V2 prime is going to be V2, the applied voltage, multiplied by R2 divided by R1 plus R2. We all know this. So V2 prime is V2 times R2 divided by R1 plus R2, and this voltage is the actual voltage applied at the non-inverting input of this op amp. And you can see, because this is grounded, only if you look at this part of the circuit, you can immediately recognize it as a non-inverting amplifier, which we discussed in the feedback configurations at the first instance. So the output is very well known. V output is equal to 1 plus R2 by R1 times V2 prime, where V2 prime is actual voltage applied at the pin number 3 or the non-inverting input of the op amp. R2, R1 are the feedback resistors, and the R1 is the input resistor. So V2 is equal to 1 plus R2 by R1 into V2 prime, but we have already seen V2 prime is obtained using the potential divider. Therefore V2 into R2 by R1 plus R2. So I combine these two. VO2 is R1 plus R2 by R1 into R2 by R1 plus R2. This 1 plus R2 by R1 is nothing but R1 plus R2 by R1 into R2 by R1 and multiplied by V2, that V2 is missing here. So if you cancel R1 plus R2, you get R2 by R1 times V2. So when I apply V2 alone, I get an output which is R2 by R1 times V2 with a plus sign here, and when I applied the first V1 alone, you get minus R2 by R1 times V1. So when I combine them together, V output is, by superposition theorem, VO1 plus VO2 minus R2 by R1 times V1 plus R2 by R1 times V2, and that means R2 by R1 times V2 minus V1, and this is the expression that we already know. V output is equal to R2 by R1 times V2 difference V1, V2 minus V1. If V2 is larger, then obviously this will be positive, and therefore the output voltage will be positive. When V2 is less than V1, then you will get a negative voltage here, and therefore the output also will become negative. Now we will perform a simulation of this difference amplifier or differential amplifier. So you have the breadboard here, you have the dual supply, and you have the two voltage sources as in the case of the summing amplifier, and you have the multimeter, and the circuit is shown here. This is the difference amplifier which we have already seen with the two input voltage R1 R2 resistors and the feedback resistor R2 and the other resistor R2 here. So you have a voltage source, two voltage sources, and the multimeter. Now let me quickly set the circuit in the differential amplifier. So you have the two resistors at the input, and this is the one which is connected from the pin number 3 to the ground. This is the one which is the feedback resistor, and they are all connected to the power supply, the dual supply, the voltage source, and the multimeter. Right, now the circuit is ready. You can see this voltage, one voltage source is coming to this input, which is actually going to pin number 2, and the other input of the voltage source is coming to the pin number 3, and then the 3 is also connected to ground, and the pin number 2 is connected through a feedback to another resistor, which is R2 here. So now let us switch on the power supply, the voltage source, and the multimeter. Everything is switched on. Now we can start giving input voltages. I give 100, because this is connected to pin number 2, I get about 10 times this value due to the gain. So, it is minus 1 volt. 100 millivolt minus 10 corresponds to minus 1 volt. If I give 200 millivolts here, or the V2, so V2 is larger, V1 is smaller, the V2 minus V1 is 100 millivolt, and multiplied by 10 is 1 volt. That is what the multimeter reads here, 1 volt. So, if I now increase V1, now it is 300 millivolts, V1, V2 is 200 millivolts, and therefore, there is a difference of 100 millivolts, but it is the minus input which is larger, and therefore, the output becomes minus. So, you can see if I make them equal, they appear to be 0, but in principle if you actually try it out on in the lab, you would find it will not be an exact 0, because 0 is very difficult to obtain. It can be few microvolts or millivolts, there will be some residual voltage, about which I have already mentioned to you earlier in the summing amplifier also, and that is both, even when both the inputs are equal to 0 or to any constant value, to 300 millivolts, both of them, still the output need not be 0, because there is always what is known as an offset voltage, about which again we will discuss at a later time. So, the offset voltage is the residual voltage that you get when you connect both the inputs to 0. In principle, it should be 0. Ideally, for an ideal operational amplifier, when the two inputs are grounded, the output should be 0. But in actual practice, you would find even when you ground both the inputs, the output need not be 0. It will have some residual value, either positive or negative, depending upon the op amp. So, therefore, even though it shows 0 here in this case, in an actual case in the lab, you would find it is not exactly 0, it has got a very small value of voltage. So, this is the difference amplifier. Now, I would like to quickly go there and show you a demonstration of the difference amplifier. Here we have the difference amplifier shown, the circuit is shown here, is the same as what we discussed already. You have the two inputs V1 and V2, and you have an output measured using a voltmeter, and this is the difference amplifier. Here all of them are with 10K, 10K, etc. So, they are the same. So, the gain here, the A is 1, because all the resistors chosen in this circuit is 1, and this actual circuit, you can see the op amp here, and the resistors, 2 resistors and the 2 other resistors are all shown here, and all of them are 10K. Therefore, the gain factor is 1. Therefore, what we expect is if I give a V1 and a V2, then the output voltage should be directly the V1 minus V2 or V2 minus V1, as the case may be. Now, the two input voltages, as we did in the earlier summing amplifier, I have used here a voltage source, which is also the one which I used earlier, which can give in millivolts, hundreds of millivolts input, and this is the corresponding voltmeter which measures the output voltage of this V1. So, these two correspond to the V1, and this voltmeter and the corresponding voltage source that I have here in the power supply, I am using it as V2, and this voltmeter here is the one which actually measures the output voltage of the difference amplifier. So, it is in voltage mode, and what it reads is the output voltage of the difference amplifier. Now, what I have kept here is 100 millivolts. I have kept here. I am sure you are all able to see 0.1 volt here, that corresponds to 100 millivolt. So, the same voltage which I applied is measured here at the input, and the other input voltage is around 445.446 voltage, or about 446 millivolts. So, 446 millivolts minus 100 millivolts should be 335 or 340, and what you get here is 0.337 millivolts, which is actually the difference between the two inputs. Now, if I increase the one of the input source, for example V1 to 200 millivolts, this reads, you can see 0.2 volts, and this is, I have not changed this, therefore, it is still 0.445 minus 2 gives me something like 0.2 something. So, that is what you see here. So, this is the difference between the two input. Now, I still increase it still further to 300 millivolts. Therefore, this is reading 0.3 volts V1, V2 is still 0.44, and so the difference is around 0.14, 0.138 is what it reads here. So, it is actually measuring the difference between the two inputs. The output is the difference between the two inputs. Now, I can also vary the other source. So, what I will do is I will reduce it again V1 to 0.1, and I will change the other input So, now the other input reads about 0.67 or something, and 67 minus 0.1 is around 0.5. So, the input, the second input V2 is 0.6 something, minus 0.1 gives about 0.5. So, if I increase it still further, you can see this is 0.2, 6 minus 0.2 is about 0.4, and now if I keep increasing it till this becomes higher. So, now I have 700 millivolt, 0.7 V1 and V2 is about 0.5. So, the difference is what I get with a negative sign, minus 0.152 or something. So, this is minus because this voltage V1 is larger than V2. So, V2 minus V1, net result is a minus, and therefore, what you get at the output is also minus 0.17 or 16. So, you can see exactly the same way that the two input voltage, the difference in the two voltages is what I get at the output, and if I want a gain, then I can always increase the value of this resistor in the circuit or and this resistor. If I make this 20k and 20k, you would find the output will be 2 times. If I make it 4 times, the output will become 4 times. So, you can also get a gain factor corresponding to the resistor. So, it is very easy to have a differential amplifier where the output voltage is the difference between the two input voltages. So, what we have so far seen is a summing amplifier, and we also saw a simulation of the summing amplifier, and we also saw how averaging can be done for the input voltages. Then we saw a demonstration of the summing amplifier, and finally, we also saw what is a digital to analog converter, how a summing amplifier can be used to construct a digital to analog converter, and then we saw what is a difference amplifier and the basic configuration of a difference amplifier using op amp and few resistance, and we also saw a simulation and a demonstration of a difference amplifier. Next time, perhaps in the next lecture, we will take up another configuration of the difference amplifier and discuss the applications of the difference amplifier, and we will move on to other mathematical operations such as integration and differentiation. Thank you.